Okay, now we are ready to discuss the KAIST exterior power of the vector space. So most of the properties will be similar, right? We have seen the second exterior power and we have seen some properties, and we're going to generalize that for KAIST exterior power. So let me start with alternating multilinear form. So V is again vector space, and alternating multilinear form of degree k on V is a function m is that defined on V to the k to the field, right? So this vector space is over a field f with the following properties. Right, so the first property is m of w1, w2, wk is 0 if wi is equal to wj for some I not equal to j. So if two coordinates are equal, then two arguments are equal, then you get 0. And the next property is when you swap two locations, so let's say w1, it's not clear how to write this clearly. Right. So yeah, so what I mean is it's minus mw1, w2, wj. So this becomes wj and this becomes wi. Right? So this moves over here, this moves over here. So if you change two of the argument, then you get negative something. All right, and the last condition is just linearity condition. So m c1a1 c2a2 and w2 w3 and wk is equal to m c1 a1 w2 w3 and wk plus c2m a2 w2 w3 and wk, right, for c1 c2 in f and w1 w2 w3 wk in f to the n. Oh yeah, I didn't, no these are functions, these are vectors in V, right? a1 a2 are also vectors in V, right? So when you satisfy these three properties, then we call it an alternating multilinear form. So the third condition says it's multilinear, and the second condition, and first and second condition, says that it's alternating. All right, now here's a fundamental property. All right, so let M be an alternating multilinear form of degree k on V, and let u1, u2, uk and w1, wk are the vectors in V. So if u1, u2, all of them are in the subspace span by w1, w2, wk, then this multilinear form, the value of this multilinear form is some constant, scalar product, constant multiple of this w1, w2, wk for some lambda in the field. Why? Because I can represent u1 as a linear combination of wi's, u2 has a linear combination of wi's, and you can expand it, right? So, and then whenever you have two coordinates of the same value, then they collapse to 0. So what's left is just all the argument over this thing, right? And that's the only choices is going to be w1 up to wk, right? If you have a different permutation, you can rearrange, right? So it's easy. Now we are ready to define the KAIST exterior power. Of V. Okay, so with finite dimensional vector space, but anyway. We write as this notation is the dual space of the vector space of all alternating multilinear form of degree k on V. All right, now we need some convenient notations. So and the wedge product is a notation to represent the vectors in this KAIST exterior power. So for k vectors, we write w1 wedge w2 wedge wk, which is in this KAIST exterior power as defined as. So this is if you remember what happened in the previous video about the second exterior power, it's similar, right? So if I give a multilinear alternating multilinear form M, then it sends it to this value, right? All right, this. Now, because it's multilinear, so if V1, V2, Vk, Vn is a basis of V, then the value of M, W1, W2, K is determined. Okay, actually M is determined by M of Vi1, Vi2, Vik, right? For I1, I2. So these are numbers from 1 up to n, right? If I know all of these values, right? For basis, if I know for any selection of k members of the basis, if I know the value of m of them, then that will determine this multilinear, alternating multilinear form, right? So that means there are n choose k values to determine m, and for each of them I have right, so, and all these things are linearly independent, right? What I mean is I can choose v1 up to vk to be like, give m of v1 up to vk to be 1, and all other choices I can give 0, and that's still alternating multilinear form. And that is actually quite easy to see. So the dimension of the vector space anyway, dimension of the vector space of the alternating multilinear form of degree k is anyway, we need only determine n choose k distinct values. So it's most n choose k, and actually it's gonna be n choose k. Let me show you why it's n choose k. But first of all, this implies the dimension of this k6 to the power is n choose k. Now it's enough to find the basis. Right? I'm gonna find you a basis, and as you can expect, is a basis of the k6 to the power. If v1, v2, v, and is a basis of v. All right, so I know that they are linearly independent. That's easy because you can evaluate, right? But anyway, right? So what I mean is, well, how do I know that they're linearly independent? Oh, yeah. That's the whole proof, whole purpose of the proof, because once they are linearly independent, then dimension is at most this value, so they must be a basis. So for one I1, I2, let's define let Wi, okay, let us define MW1, W2, WK, so that if Wi is linear combination of Wij, Vj, then Mi1, I2, okay, Mi1, Ik. So this is defined as determinant of W1, I1, and okay, let's W Okay, let me think. W1, I2, okay, W1, I2, W1, I3, W1, IK. So I only look at the coordinate values of I1 up to IK and make a determinant. W2, I1, W2, I2, W2, I3, W2, IK, and WKI1, WKI2, WKIK. All right, so that's a function defined from W1 up to WK to some value in the field. Now it's easy to see that M, I1, I2, IK is an alternating multilinear form of degree K. Why is it alternating? Because if I change two coordinates, let's say Wi and Wj, then determinant value will be the negative of the original determinant value, right? So we can multiply -1 and nothing changes, nothing else changes. And why is it multilinear? Because if I say W1 is a linear combination of two vectors, then determinant also is multilinear. And furthermore, this is the crucial property. So if I put Vi1, Vi2, Vik, then this is determinant of identity matrix, so that's 1. And if I have a one like J1, okay, Mi1, I2, Ik, and Vj1, Vj2. So if I have a different indices, so I1, Ik is different from J1 up to Jk, then this is gonna be 0 because one of the row will be 0, right? So determinant will be 0. So if there's a linear combination okay, if J1 up to Jk and Vj1, wedge Vj2, wedge Vjk is 0. So if they are linearly dependent, then I can assign the mi1 ik, and the argument that what I get is this evaluation of this alternating multilinear form with the Vj1 up to Vjk, and the only time this is non-zero is when I1, I2 are equal to J1, J2, etc. So this is alpha I1, Ik is equal to 0. So Vi1 wedge Vi2 wedge is linearly independent. And if they are linearly independent, and dimension of whole thing is a most anxious case, so therefore they are bases. Okay. Now let's see some properties of the wedge product. Okay. All right. So the first one, Okay, let me change the indices. The v1 wedge, v2 wedge, vk wedge is 0 if vi is equal to vj for some I different from j. Why? Because if you want to see why this is true, you can evaluate any alternating multilinear form with the v1 of the vk. And if two of the values and two of the vectors are same, then the alternating multilinear form will give you the value 0. So even if you replace with the 0 elements of this dual space, you still have the same thing, right? So that's because so this property is implied by these definitions, the first part, right? Second property, v1, v2, v okay, again this okay, vi and vj and up to vk is equal to minus v1, v2, and vj. It's difficult to write here. So this, they change the locations, right? So when you change two of the ordering of two elements in the wedge product, then whole thing is same except you put -1 in front. And that's again implied by the second property of the alternating multilinear form. Now, third property, this is important. So let me put it as a lemma. v1 wedge, v2 wedge, vk is non-zero if and only if these vectors form is linearly independent. Why? If they are not linearly independent, if they're linearly dependent, then it can be easily seen that this is 0. Why? Because some of the vector, let's say v1, I mean, this is some linear combination of some is 0, and you can write, let's assume by symmetry that let's assume that v1 is a linear combination of others, and you can write v1 as a linear combination of v2 up to vk, and then you can expand, and then by the first property, like you have sum of the zeros, right? By this property, you have sum of the zeros, so that's easy. Right? So easy. So what if these are linear dependent, independent? Then extend it to a base, right? v1 up to vk, and then vk plus 1 up to vn. I'm assuming that v is a finite dimensional vector space. Maybe I should have said, where is it? Finite dimensional. Right? Once you expand it, then this is an element of basis, so it's a non-zero. So obviously it's non-zero. I mean, another way of saying it's non-zero is to evaluate it with this multilinear, alternating multilinear form mi1, I2 up to ik, right? Where this is defined from v of these v's, right? All right. Now, and what do we know? And wedge product and determinant, how they're related. Why? So imagine that I'm computing wedge product of these n vectors, and let's say wi is the wij and vj. So the n6 real power. Now let's apply all the rules that we know. So it's w1 1jvj, w2jvj, and wnjvj. Right? Now, if we expand it, then we have a permutations. I mean, the thing is, now if we completely expand it, then there's no need to worry about the case when you have a vi wedge vi somewhere, right? Because if two coordinates are equal, then you get 0. So the only time that it survives is when you select the sum, right? So w1, let's say I1, w2, I2, wn, in, and then vi1 wedge vi2 wedge vin, where I1, I2, these are just permutation of 1 up to n. Now, when you have a permutation, you want to make it a simple permutation. So, like, we want to permute things so that you have a v1 wedge, v2 wedge, vn. Right? But when you permute, you multiply -1. So what is how many times do you have to permute? Then there's a parity. And that's the sign of the permutation. Right? So w1, I1, and wn, in, where so sigma is a permutation. Oh no. Right, so sigma okay, I should say w1 sigma 1, w2 sigma 2, wn sigma n, and sigma is a permutation. And this is precisely, what is it? It's determinant. This part is determinant of w v1 times v1 h v2 h, and here this is the an element of basis of n6 to the power, and then this is a base that's dimension 1 vector space, and determinant of w where w is really like this matrix w11, w12. Right, so n6 to the power gives you the determinant. All right. Okay, now I'm going to define a wedge product that links vectors in two exterior powers. So for so for A here and B here, we define A wedge B. Right? How do we define that? Well, first of all, what we're gonna do is again, this is in the K plus L's exterior power, and how so this we need to map any alternating multilinear form of degree K plus L to an element of F. Right? How do we define it? Well, what we do is the following. Right. So what we look at is for so for let's consider L vectors in V. Now I'm gonna restrict M to this WL. What is that? That is M. So first K arguments are still same, but the last L argument are fixed at the WL, W1 up to WL. Right? So here M is alternating multilinear form of degree K plus L. Right? So what is this? What I mean is, if M is an alternating multilinear form of degree K plus L, then MW1 up to WL is an alternating multilinear form of degree K, because I'm fixing the last L values. All right. Now, so this is function from V to the K to F. So now, if you apply A with the M of W1 up to WL, right, then this is some value in F. Right? Because this is A is a vector in the k6 degree power, and whenever we have an alternating multilinear form of degree k, then it maps it into a value in the field. So we define A wedge B of M as what? Now, B of we define this way. What do you mean? What do you mean? Well, what I mean is, you can think of A, M, W1, WL. Let's say, let N of W1, W2, WK be the A of M, W1 up to WK, right? Then N is an alternating multilinear form of degree K. So B of N is defined, right? So that's what I mean by this. So the A wedge B is well defined, right?
There was a typo in the previous video, so these numbers should be L instead of K, right? If I write this notation, that's a multilinear polynomial, no, alternating multilinear form of degree K, right? So this is the correct form.
Now you may wonder how can you easily see this? Well, one way to see this is, the whole purpose of this kind of definition is to make the following is true. If U1 wedge UK, so this is a vector in K6 to the power, and W1 up to WL, that's a vector in L6 to the power, then what end up is our definition naturally gives you this vector. Why? Because we are evaluating first K argument to be U1 up to UK, and last L argument to be the W1 up to WL, right? So this is what we have. So the wedge product between the two vectors, one from the L6 to power, K6 to power, and the other from L6 to power, is well defined. Okay. Now a few properties. So for instance, A wedge B. So let's say A is in if A is in the K6 to the power and B is in L6 to the power, then A wedge B, okay, that's B wedge A. We need to multiply -1, but how many times do we have to multiply? It depends on how many times we actually swap, right? If I want to send everything in A side, like if I want to send here and there, right? I want to swap, right? How many, like each time I swap, I multiply something. And no matter how you swap, you end up with the same parity with the K times L, -1 to the K times L. Well, how can you see that? One way to see it is, well, for pick each one, and then you swap with this guy, you want to insert over here, right? So each time we move one from there, every element here move to backwards, right? So for each of the L elements, you're swapping K element, right? So when I do this, for instance, 1, 2, 1, 2, 3, 4, 5, 3 goes here and here, right? So 3, 2, and then 3, 1, 2, right? So this is how you can move, and without changing the order of this is A and here's B. So that's first property, and second property is easy one. So linear combination expand, so it's still multilinear. And third property is a associative, right? So here A is in the K63 power, P is in L63 power, and C is in okay, let's say M63 power. All these things are easy because you can think of the evaluation of the so this is in K plus L plus M63 power. You can think of the evaluation of the alternating multilinear form of degree K plus L plus M. Well, the some arguments are restricted. All right, that's it. Now we are ready to do something with these tools. And now we build all the definitions and terminologies and tools. Probably, and we only need to use these properties and the dimensions. Remember, the dimension is n choose k. This is the dimension, the basis of that. So dimension is precisely n choose k. That's the only thing we're gonna use in the remaining. Okay.